In the world of cloud-native development, we often treat containers as if they are practically free. We're told that because containers share the host kernel, they offer near-native performance. While this is largely true for CPU and memory allocation, networking is a significant exception. When you move a process into a container, you aren't just wrapping it in a security boundary, you are placing it behind a complex, multi-layered virtual network stack. This abstraction comes with a measurable cost in latency, throughput, and CPU utilization. Today, we're looking past the marketing slides to understand the hidden mechanics of virtual Ethernet pairs, bridge interfaces, and why your high-performance database might be losing 15% of its throughput to the very network stack that's supposed to be invisible. To understand the cost, we have to look at the plumbing. Every container sits in its own network namespace. To connect this isolated namespace to the host, Linux uses a veth pair, a virtual Ethernet cable with two ends. One end, usually named eth0, stays inside the container. The other end, often starting with veth, sits in the host's root namespace. Every packet sent by your application must traverse this virtual link. This isn't just a simple pointer handoff. It involves the kernel moving data across network boundaries, triggering soft interrupts, and potentially performing memory copies. While a single veth pair is fast, the complexity grows as we add more layers like bridges or overlay networks. You are essentially adding more hops, even if the traffic never leaves the physical machine.
In the Docker or Kubernetes setup, packets don't go straight from the veth to the physical cart. They go through a bridge, a virtual switch like Docker 0. This is where the real performance tax is paid. Because the bridge operates at layer 2, the kernel has to perform lookups to determine where to route the packet. Worse, if you're using standard port mapping, every packet must pass through netfilter and itables for network address translation, or not. This adds a processing delay to every single round trip. For a request-heavy microservice, these microseconds compound. We are no longer just running a process, we are running a mini router inside the kernel for every single container we spin up.
Let's look at the numbers. When comparing native performance to container bridge mode, the throughput drop is usually manageable, around 5 to 10%. However, the latency story is different. In high concurrency scenarios, P99 latency can spike by 20% or more due to lock contention in the virtual bridge. In this table, we see the stark difference between host mode, where the container shares the host's IP directly, and the default bridge mode. Host mode is nearly identical to native performance because it bypasses the virtual plumbing entirely. If your application is sensitive to sub-millisecond jitters, like a high-frequency trading engine or a real-time cache, the default bridge is your enemy. The most hidden cost isn't network speed, it's CPU cycles. Networking is a CPU-intensive task. For every packet, the host CPU must stop what it's doing, handle a soft interrupt, and process the packet through the stack. In a containerized environment, the CPU spends significantly more time in kernel space than in user space compared to native execution. This is the system time you see in top or htop. You might find that your application is scaling poorly, not because the code is slow, but because 30% of your CPU is busy just moving bits between namespaces. This effectively lowers your compute density, meaning you need more servers to do the same amount of work.
So how do we fix it? The first step is awareness. If you have a trusted, high-performance service, consider using host networking to bypass the bridge entirely. But in multi-tenant environments like Kubernetes, that's often not an option. This is where modern technologies like eBPF come in. Tools like Cilium use eBPF to short-circuit the kernel stack. Instead of a packet traveling through the full bridge and IP tables machinery, an eBPF program can identify the destination and jump the packet directly from one veth to another. It's like replacing a winding city road with a direct tunnel. It reduces latency and saves CPU cycles, bringing container performance back toward native levels.
To wrap up, containers are lightweight, but their networks are not. For most web apps, the bridge overhead is negligible. But for databases, caches, and high-throughput proxies, the network is your most expensive component. Measure your system time, test host mode performance, and look into eBPF-based networking if you're hitting a wall. Understanding the hidden plumbing of the Linux kernel is the difference between a system that scales and one that stalls. Thanks for watching.